Okay, so this is some work to support electrostatics, to help you with some physics if you've forgotten it or you didn't know it. And we're going to look at electrical charges, electrical fields, and electrical potential. And the topic of electrostatics has been chosen because it's so useful to chemistry students. If you need to, you can make notes on, but you need to revise and be familiar, I think, with the following terms. Electrical charge, that's always given the symbol Q, sometimes uppercase, sometimes lowercase, and the unit is the Coulomb, named after a French scientist, and more about him later, and the symbol for the Coulomb is just a capital C. Forces between charges we'll be looking at that as well. Forces, they was abbreviated to F, and the unit, the Newton, and the symbol for the Newton is just an uppercase N. We'll look at electrical potential, that's given the symbol V, and that's got the units of joules per coulomb. You might be confused with V being voltage, and we'll see that 1 joule per coulomb is 1 volt. There's a connection between the two. We'll look at electrical fields. Electrical field strength has got the symbol E, and it has the unit of newtons per coulomb. So it's the force that a charge experiences when it's placed next to another charged object, and we'll look at that. And we'll have a little bit of a think about electrical dipoles, obviously very important to scientists, polar bonds and so forth. So that's electrical dipoles, mu, the Greek letter used there, and it's got the units of coulomb meters or Debye units. Electrical charge, first of all. Amber rubbed with a cloth can pick up bits of paper, and the ancient Greeks noticed that. This has been well known for a long time. And the Greek word for amber is electra, which is where we get electricity from, an electron. Benjamin Franklin, very clever man, been dead a while, died in 1790, but he decided that the charge gained by rubbing a glass rod would be called positive. And if you rub some amber, that gains a charge as well, and he would call that negative charge. And we're left with those two terms, electrical charge is positive and negative, as a result of a decision made by Benjamin Franklin a very long time ago. Charge is quantized. It can't have any value. It breaks down to sort of goes up in steps. And if you have a positive charge, then the whole point is that this object has got less than its balanced number of electrons. And if you've got a negatively charged object, then it has an excess of electrons. And you will need to know that the charge on an electron is this value here, minus 1.6 times 10 to the minus 19 coulombs. It's not nerdy. Try and learn it. It's important. Okay, a positively charged object here and a positively charged object here. Clearly, that charged object is going to feel a force. It's going to want to move somewhere or other. And you should remember or know that oppositely charged objects attract, and that objects with the same charge will repel. And so this object here is going to want to go in that direction, off to the right on our screen. E, the capital letter E, it stands for electrical field strength. That charged object, we'll give it the symbol Q, lowercase q, to denote the fact that it's charged. And the force that this object feels, placed here, obviously it wants to go in this direction, the force it feels is somehow proportional to the charge that it's got. The more charged up that object is, the stronger the force. And you should know that, or if you don't, you're about to, that a constant of proportionality like this one can be got rid of by adding an equal sign and a constant. And so you get a formula this way, that force is equal to the electrical field strength multiplied by the charge on the object. F equals EQ. Often rewritten, if you look it up in physics books, I recommend just a good A-level physics book if you want to back this sort of thing up. It's often written as E, electrical field strength, is equal to force divided by the charge. E is F over Q. If we go back to the way we've written it here, force is equal to EQ, let's make sure that we're happy with some fairly important units and whatnot. So force is always given the unit newtons. Electrical field strength, well, that's the force that the charged object experiences when you place it next to that bigger charged object in our diagram. And so electrical field strength has got units of newtons per coulomb. It's how much force it feels for the amount of charge it's got. And you'll find that Q, well, that's charge, and that's got the unit coulombs. And I've just clicked too many times there, but Newton is always abbreviated to capital N. Newtons per coulomb is N over C, sometimes written as this, of course. Newtons to the coulomb to the minus 1 means the same thing. and Coulomb's is abbreviated to capital C. The Coulomb, funny word, named after Charles Coulomb, and again, he's been gone a while too. He died in 1806, but he was very interested in this, and this is some very famous physics as well. If you place two charged objects together, Q1 and Q2, they have opposite charge, they're going to be attracted. The positive charge is going to want to move towards the electrical charge. Well, they're both going to feel a force of attraction there. And so what we have here is some idea of what does that size of the force, what does it depend upon? How strong is that attraction? Well, it's an empirical rule, in other words, it's based on experiment, and what Coulomb observed was that the size of both charges multiplied together, the product of the charges, is important. The bigger that number, the stronger the force between the two charged objects. Also, their separation is important. If you place the two charged objects a long way away from each other, then there's a very weak force between them. If you place them close together, there's a strong force between them. However, he went further, and he noticed that the size of the force varies in quite a clever way. It's proportional to the inverse square of their separation. It might help if I just show a little graph here. So what you'll see is that if you place two objects very close together, like here, then the force is large. But that size of that force drops very quickly as you separate the forces away. So as you can see, that there's this curve, an inverse square. Slight change in separation, big change in the size of the force between them. So a physics book might show you something like this. Remember that this sign here, that's the constant of proportionality. So the force that the two objects are feeling is proportional to the product of the charges upon them divided by the square of their separation. And remember that you can get rid of that constant of proportionality sign by introducing an equal sign and a constant, as we have here. So you can say that the force between the two charged objects is equal to some constant multiplied by the product of their charges divided by the square of their separation. K's got a number, 9 times 10 to the power 9 newtons metre squared divided by Coulomb squared. Don't worry too much about that. One Coulomb, we're talking about the unit of charge, 1 Coulomb. In fact, 1 Coulomb is a big charge. If you placed two charges a metre apart and there was they had a 1 Coulomb charge, and they had an opposite charge, they'd be attracted together with a force equivalent to 9 million tonnes. So in chemistry, we're not really interested in whole coulombs. The charge on an electron, please learn it, I said that earlier, minus 1.6 times 10 to the minus 19 coulombs. Tiny, tiny, tiny amount. So 1 Coulomb is big. Okay, going back to this then, force between the two charged particles is equal, or is proportional to, the product of their charges divided by the square of their separation. So we showed you this just a minute ago, and then you introduce an equal sign and a constant. Now, in fact, K can be derived mathematically. K can be derived as 1 over 4 pi epsilon naught. And this is epsilon naught here. It's got a name, the permittivity of free space, and there's a number associated with it, which is just down here at the bottom of your screen. And so you can substitute the K we see here for its more expanded form, and you end up with this equation here. Force is equal to the product of the two charges in coulombs divided by 4 pi epsilon naught over r squared. The point of showing you that is please don't be frightened by awful looking equations like this. 4 is a number, pi is a number, and epsilon naught is a number as well. And so all of this is a constant, and you can tie it back up to this one here. It's an unchanging value. It looks scary, it's not really. Just go back one there. That's called the Coulombic force, F. Okay. On to electric fields now. We hear the term electrical fields a lot. Well, what on earth do they mean? Well, it confused a lot of people, and it was a man called Michael Faraday, this is Faraday here, who came up with this idea. Forces are easy to imagine if they work directly on an object. If you're pushing this little cart here, it moves along. That's easy for us to understand. Well, what we seem to have with electrical charges, and also magnets, so we're not going to talk about that, is that you can apparently move things even though you're not touching them directly. Action at a distance was the term coined for that, and that bothered even Newton. And so how does that happen? Newton wasn't happy with that either. Well, Michael Faraday created the concept of an electrical field. 1791, 1867, there he is down there, Faraday, a great mind. An electrical field is this idea. It's a region of space inside which a charged object will experience a force. And you may have just seen that little animation there, that this little negatively charged thing here will move towards this one because an electrical field is emanating from this charged object. And this was a concept invented by Faraday. If you put a tiny positive test charge, which we use the symbol lowercase q for, in a field, it experiences a force. It moves towards or away if it's depending whether the charges are opposite or the same. And the size of this force that it feels is equal to the size of the charge multiplied by the magnitude of the electrical field. And so force is equal to the size of the charge of the object we're interested in, on the object we're interested in, multiplied by the electrical field strength at that point. And we've just seen that, we've just done that in the last bit, that E is equal to F over Q. That's just that equation there being rearranged. You may notice that we've written E in bold, and that's to show you that it's a vector quantity. It's got both size and direction. More on that later. We've just done this, but it doesn't do any harm to recap. Electrical field strength has got units of newtons per coulomb. It's the force on a charged object in a field. The definition of electrical field is the force per unit charge. Okay, so I find that very helpful to remember. E, newtons per coulomb. It's always a good thing to try and remember units for things. Now, Coulomb's law gives us a useful formula for electrical field. Here's the larger of the two charged objects, and there's our test charge here. And so we've got this formula that we're happy with, that E is equal to F over Q. And this one here is the same formula. We've just drawn them out, okay? So F times 1 over Q. That's the same as F over Q. And we know that the force that this little object is going to feel is equal to some constant, a number, multiplied by the product of the two charges in coulombs divided by the square of their separation, the coulombic force between them. Rewatch the earlier bit if you've forgotten. Now, we know that E, electrical field strength, okay, it can be now rewritten in this form. Now, that might be beginning to look a bit scary, but all we've done is a little bit of substitution. Look, we've said that E is F times 1 over Q. And so if you see what we've done here, the force can therefore be written as the constant times the product of the two charges over r squared. Well, let's just substitute this F for this here. In other words, we're substituting all of that for that. And when we do so, we get this new formula. You can cancel those two charges, the lowercase q's, they appear in both, and so they disappear. And you end up with a very important formula, which is this. The electrical field strength at a point is equal to some constant, just a number, times the charge on the object that is generating the electrical field, divided by the square of the distance you are away from that object. This is interesting because it's telling you, I'm just going to come to this bit here first, the electrical field strength, the size of that, depends only on the magnitude of the charge on the object that's producing the field. That's the only thing that matters there. It's not involving the little point charge that you put into the field to see what happens. Okay, back to this then. So we have the fact that E is equal to some constant times the charge, the big charge generating the field, divided by the square of the distance from it. If you want to, and you look it up in a physics book, you might see this formula and you think, oh, what on earth is that? This looks different. Well, what it is that K is often written in this form here. And so you'll often see that there's 1 over 4 pi epsilon naught incorporated into that form. It's the same thing, it's just a constant. So you can also see, just going back here, if you draw out this term, the electrical field strength around that charged object varies as a function of the inverse square of the distance. In other words, if you go a little bit further away from that charged object, then the size of the electrical field strength at that point has dropped a lot. Okay, there's a big variation. Remember that inverse square gives you that kind of shape, okay? In this case it would be E and R like that. Electrical field is a vector, and to show that, just to reiterate, it's either written with a bold type, or if you go to your textbooks you may find that they draw the thing with an arrow above it. And please remember, vectors have got both magnitude, size and direction. it always helps me to think of E, electrical field strength. You can forget what these terms mean. Just remember the unit. It's the force per charge. In other words, you put a little charged object next to this other charged object, it will move. It will move away or towards, and it's the size of that force. Okay, that's what it's helping us to work out. A little bit for you on electrical field lines or lines of force. They're always drawn from high to low potential, and more on potential in a moment. It's a way to show the electrical field at many different points. So point charges, we've already seen this in the material we were just doing. We're seeing that the electrical field lines radiate away. If you take two equal charges of opposite sign placed a certain distance apart, two equal charges a certain distance apart, that's called a dipole. That's where it comes from. Well, it might remind you a bit of the magnetic field lines actually, but it's this pattern you see here. They show the direction a force would act upon a tiny positive test charge that you place at a certain point. I'll show you. And the direction that little tiny point charge would move, if you placed it at that point, is tangential. It's a tangent to the field line at that point. And so I think that's quite clever, really. If you place a little point charge here, it's going to move in this direction because that's a tangent to that curve at that point. All clever stuff. The closer the lines are, the stronger the field. Look, here, close to that charged object, the lines are much closer than they are, say, here. They're sort of spreading out. I don't know how well my diagram's showing that, but it's what we'd expect. The further you are away, then the less strong the electrical field is. A capacitor, two charged plates a certain distance apart. If you've forgotten what a capacitor is, it's a device used for storing charge. Very common electronic component. You see that there's field lines between them. A point positive charge inside a spherical anode, you get this sort of cartwheel effect. It's going from the positive to the negative. And a point positive charge in a flat negative electrode anode. You get this pattern here. Might be useful to memorise if you think that thing there might be an electrode and this thing here could be an ion, electrolysis. A little interesting note, we're getting into Nerdsville here, but there's no electrical field inside a conductor when the charges are at rest. Okay, so if you've got a charged up object, there is no electrical field inside it. No force acts upon the free electrons. They aren't flowing anywhere, they're just existing. And so the charge must be distributed, if there is any, there's an electrical charge on that object, it has to be distributed over the surface. So put that in plain English, Nick. There's no electrical field inside a charged object. The charge is distributed over the surface of it. I find this interesting, so I'm going to share it with you because I like to be able to put things in context, and I hope you like it as well. We use all these words, we've been taught them, and you know, electron, neutron, proton, charge, and so forth, and it's interesting to see where they come from and who the great minds were, or who the great people were that worked all this stuff out. The electron, well, that was discovered in 1897 by Sir Joseph Thomson, J.J. Thomson, and he won the Nobel Prize for that in 1906. You then had that fascinating bit of science where they demonstrated electron diffraction. If you fire a beam of electrons through a diffraction grating, maybe two narrow slits, they spread out and you get diffraction patterns. They're behaving like a wave. Worryingly, that was J.J. Thomson's son, and he won the Nobel Prize to demonstrate electron diffraction in 1937. So Dad, Nobel Prize for discovering the electron, son, Nobel Prize for demonstrating the wave nature of electrons. Nuclear model of the atom. The atom has a little nucleus and the electrons are around the outside of that, 99% empty space. Well, don't go too far, but this is you know, about looking all the modern understanding of atoms, but the nucleus in the middle are mainly empty space. That was Ernest Rutherford, 1906, for which he wins the Nobel Prize in 1908, and he was assisted famously by Geiger and Marsden. Geiger as in the Geiger-Müller tube, that's Geiger again, the radioactivity detector. Marsden, he was an undergraduate when he worked with Rutherford on that. 1913, a man called Henry Moseley, he showed that an element's place on the periodic table is equal to its nuclear charge. He should undoubtedly have won a Nobel Prize for that, a monumental piece of work. But if you look at his lifespan, he died very young, 1915. That was the Battle of Gallipoli, and he was shot by a sniper. And you don't win Nobel Prizes if you're dead. In 1919, Rutherford showed that I should word that better, they don't award Nobel Prizes posthumously. There you go. 1919, Rutherford showed that the hydrogen nucleus is present in other elements. It's usually described as the discovery of the proton. Might link that to NMR, perhaps. We talk about proton NMR. It's just the hydrogen nucleus that we're thinking about. Anyway, the proton, 1919, Rutherford again. Charge on the electron, minus 1.6 times 10 to the minus 19 coulombs. See, I know it. Robert Millikan, 1917, Nobel Prize, 1923. How recent it is, really, just early 20th century. The discovery of the neutron, which we're also happy with, uncharged particle, equivalent mass to the proton in the nucleus, isotopes and all that. Well, James Chadwick, 1932, for which he wins the Nobel Prize in 1935. A little bit now on electrical potential, given the symbol V. Uppercase V, lowercase is normally velocity. So the electrical potential energy per unit charge. Right. If you place a charged object here, Q, and you place it some distance away from this other charge-generating source, okay, another charged object, then that object really wants to go in that direction. It wants to clear off. It's being repelled. If you push it this way, you have to use energy. You're going to do work, to use the terms of the Industrial Revolution, really. And its electrical potential energy increases. Let's put that in plain English for you. If it's here, that charged object wants to move off in this direction, to the left of the screen. If you were to move it here, you had to use some effort to do that. Energy was required to do that. But if you let go, it would go off to the left of the screen much more quickly. It's got greater potential. It really wants to move now, and so its electrical potential has been increased. V you normally associate with volts, and 1 volt is 1 joule per coulomb. Okay, more on this now. The volt and potential difference, in other words, potential difference, you might remember, you might know, potential difference, PD, is an alternative term for voltage. If you have the object here, as shown, it's got a certain amount of electrical potential energy. If you move it closer, it's got a different amount of potential energy. It's more now. If you move it further away, it's a different amount of potential energy, now less. So if you apply a force and you move that point charge closer, so it's gone from a place where the electrical potential can be described as V1 to a place where its electrical potential can be described as V2. So its electrical potential has changed. There is a potential difference between being here and being here. There's a potential difference. Voltage is going to be invoked in just a minute. The work that you do, you may remember this, if not, you need to know that work done is equal to a force multiplied by a distance. And so in our diagram, the distance is a tiny, tiny change, and so we use delta R, okay, small change in displacement, delta R, delta, tiny little bit. So work is force times delta R, F delta R. The work done, the energy transformed, you can't say used up, remember, energy transformed, changed from one form to another, in moving this unit positive charge is numerically equal to the potential difference between the 2 points. So work done, that we end up with this formula, is the charge, Q, multiplied by the potential difference, V. I'll come back to this. If it takes 1 joule of energy to move 1 coulomb between the points here, where the 2 dashed red lines, this distance, move it across here. If it takes 1 joule to do that, you've moved 1 coulomb, you've expended 1 joule per coulomb, then the potential difference between where it started and where it finished, the potential difference between those 2 points is defined as 1 volt. In a uniform field, this of course is a capacitor, these 2 charged plates, with a separation D and a potential difference between them, capital V. There's a useful little formula. You can go and do some more reading about this, but here's a useful formula. It can be shown that the magnitude of the electrical field intensity, E, is given by this equation. It's the electrical potential divided by the distance, the separation, and it gives you a potential gradient, voltage per meter. Okay, there's a little bit of stuff on electrostatics for you.